Hello everybody, welcome back to my channel. How about a review in dynamics this week? So we're starting with particle kinematics. And the problem says the position of a particle is described by the position vector 3t cubed minus 2t squared I plus 4t squared plus 2tj plus 6t cubed minus 2t squared plus 3t k. What are the magnitude of the velocity and acceleration at t equals to 5 seconds? First, I would like, as always, to go to FE Handbook and locate our formulas. So we're going to go to Dynamics. There you go. And here we have particle kinematics. And the formulas that we're going to use are over here. So eventually, this is the position vector, this is the velocity vector, and this is acceleration vector. And what this tells us is that the velocity vector can be obtained by taking the first derivative of the position vector. And then the acceleration vector can be obtained by taking the second derivative of the position vector. So this is what we're going to do in this problem. Let's first, I'm going to write the position vector, which in our case is, I'm going to say x equals to 3t cubed minus 2t squared I plus 4t squared plus 2tj plus 6t cubed minus 2t squared plus 3tk. So this is our position vector. Now we need to find the velocity vector. And we know velocity vector is nothing else but first derivative of the position vector. So let's do just that. We're going to have 9t squared minus 4t. There you go. And then here we're going to have 8t plus 2j. And then we're going to have 18t squared minus 4t plus 3k. Next, we're going to do the same with the acceleration vector, which is nothing else but the position vector, or the second derivative of the position vector, or we can also say is the first derivative of the velocity vector. So let's go ahead and find out what is the acceleration vector. We're going to have here 18t minus 4I plus 8j plus 36t minus 4k. There you go. So now we have both vectors. Now the problem is asking what are the magnitude of these two vectors. So in order to calculate the magnitude, we're going to have to do the following. At t equal to 5 seconds, velocity vector equals 2. And we're going to take this velocity equation and we're going to replace t with 5. Let's do that. We're going to have 9 multiplied by 5 squared minus 4 multiplied by 5. This is I plus 8 multiplied by 5 plus 2j plus 18 multiplied by 5 squared minus 4t plus 4t. Excuse me, this is going to be 4 times 5 plus 3k. And once you do all the calculations, you should get that the velocity vector, let's do results, and then the result v equals to 205I plus 42J plus 433K. So now we have the velocity vector, and we can calculate the magnitude of the velocity. And the way you do that, let's say magnitude of the velocity equals 2, and we take square root of 205 squared plus 42 squared plus 433 squared. And if you use your calculator, you should get a result of 480.9. So approximately 481. Now, see, especially when you're on the exam, you want to check the results and see if you have any results of 481 showing up. And I know I'm noticing that option A is giving me 481 for the velocity. And then there's not any other option giving me that, which on the exam, in order to reduce spending as much time on the problem, I would just go ahead and choose option A. But I'm going to continue to make sure that the acceleration is 196. So let's go ahead and do the same for the acceleration. I'll say at t equals to 5 seconds, the acceleration equals 2, and we're going to come back to this equation now, and we're going to substitute t with 5 multiplied by 5 minus 4I plus 8J plus 36 multiplied by 5 minus 4K. And now doing all these calculations, you should get that A is equal to 86I plus 8J plus 176K. And now the magnitude of acceleration equals 2, and we're going to do square root of 86 squared plus 8 squared plus 176 squared, and this is going to give you a value of 196.1. So indeed, option A is the correct answer. Radial and transverse components for planar motion. So an airplane's path is tracked by a radar using the distance RT and angular elevation theta t. Functions given below are measured in kilometers, theta measured in radians, t in seconds. At t equals to 5 seconds, what is the speed of the aircraft? The first note I want to make is whenever you do your calculations, especially angle calculations, I'm noticing here radians, so make sure you have your calculator in radian mode. So let's go again. We're going to work hand in hand with the FE handbook and radial and transverse components for planar motion. So these are the formulas. We have the formula for displacement, velocity, and we have acceleration. In our case, we have to calculate the speed of the aircraft. So we're going to use the formula for the speed. Let's write it down. So we have V equals to, have first the derivative of R, ER plus R, first derivative of theta, E theta. So we have the distance RT, and we have the angular elevation theta t. All we have to do is take the first derivative of the R and substitute it in this equation. So we're going to do just that. So first derivative of R, 5.2, it's going to be 0. We're going to get 0.08 minus 0.1 t. So this is our first derivative of r, er, plus, now we're going to write the distance equation, which is 5.2 plus 0.08 t minus 0.05 t squared, and then multiplied by first derivative of angular elevation, theta. So we're going to take first derivative of this equation now. 1, it's going to become 0. Next, we have 0.01 plus 0.02 t, close parenthesis, e theta. So this is the equation we end up with. And now, moving forward, we have to calculate what is the speed at t equals to 5 seconds. So we're going to repeat the steps we did before in previous problem. We're going to say that, let's say, at t equals to 5, v equals 2, and we're going to come back to this equation, say v equals 2, so this equation over here, and we're going to substitute t with 5. Let's do this. 0.08 minus 0.1 times 5 er plus 5.2 plus 0.08 multiplied by 5 minus 0.05 multiplied by 5 squared. Then open another parenthesis, 0.01 plus 0.02 multiplied by 5 e theta equals, and come back here, equals. Once you do all the calculations, you should get the following vector. This is going to give you minus 0.42 er plus 0.48 e theta. And now this is our velocity vector, and we have to calculate the speed. We're going to take the magnitude of this velocity vector. It's going to be equal to minus 0.42 squared plus 0.48 squared. Let's close this square root. And after you do all the math, you should get that the magnitude of the velocity vector is equal to 0.638. And these are kilometers over seconds. The units for all these solutions are in kilometers per hour. So we're going to have to transform into kilometers per hour. So we're going to say that 1 hour is equal to 3,600 seconds. So now seconds and seconds go away, and we're left with units kilometers per hour. So let's do the math here. 3,600, 0.638 multiply gives me a value of 296.8. And of course, these are kilometers per hour. This is the correct answer. And the closest between all the options here is 2,300. So D is our correct answer. Great. So you notice how we just used the formula provided in the FE handbook and substituted, and then we got our answer. Moving on. Normal and tangential components. A car is traveling at the crest of a hill as shown below. At the crest, the hill has a radius of curvature of 240 meters. If the tangential velocity equals to 120 kilometers per hour and acceleration equals to 1.39 meters per second squared, what is the total acceleration? Okay, so if in the problem it is mentioned the tangential velocity, that means that we are dealing obviously with normal and tangential components. So going back to the FE handbook, you can either type normal or tangential components, or if you know where they are, you can scroll down and find them. So the formulas we're going to use here, we have the formula for acceleration. Notice how acceleration is equal to the tangential acceleration, and then you have this formula vt squared over radius of curvature, and this is nothing else. This is normal acceleration. And you don't have to remember that. This formula is given some, oh, there you go. This is the same thing. So normal acceleration formula is over here, and is v squared over radius of curvature. And then there's also a formula for the radius of curvature over here. Sometimes the problem might ask you to calculate it. So you have the formula here, you don't have to memorize it. In our problem, going back here, we have to calculate the total acceleration. So in cases like this, we have the speed, and then the tangential acceleration is pointing in this direction, and then the normal acceleration, it's pointing towards the center. And the formula says that the acceleration vector is going to be equal to, we have AT ET plus AN EN. And this means that if we have to calculate the magnitude of this vector, we're going to have square root of AT squared plus AN squared. So this is what we have to calculate, the total acceleration. Now, going back to what the problem is providing us, we have radius of curvature. So let's write down. We are given, let me write it here. So this is equal to 240 meters. Next, we have tangential velocity. So we have V is equal to 120 kilometers per hour. And also we are given, this is tangential acceleration equals to 1.39 meters per second squared. So the only thing we have to calculate or find out is normal acceleration. And remember, there you go. Normal acceleration formula is actually Vt squared over radius of curvature. So let's write this down. An is equal to V squared over radius of curvature. Now, let's come back here for a bit. I want to transform velocity from kilometers per hour into meters per second to make my calculations a little bit easier. So what I'm going to do, I'm going to say, let me delete the equal sign. So in order to transform this into meters, I'll do 1 kilometer equal to 1,000 meters. Okay, and then 1 hour is equal to 3,600 seconds. And now hour with hour goes away, kilometer with kilometer goes away, and the final units are in meters per second, which is what I want. So I'm gonna have 120,000, 3,600 divided. I'm getting a velocity of 33.33 meters per second. Perfect. So now I can use this velocity into my equation and say 33.33 meters per second squared. And then I have the radius of curvature in meters. So normal acceleration is 4.6 63 meters over seconds squared. So now we have everything we need to calculate for the total acceleration. I'm going to come back here and I'll say total acceleration is equal to square root of tangential acceleration, which is 1.39 squared plus 4.63 squared. And this gives me a total acceleration of 4.83 meters per second squared. And this is the correct answer. So C is the correct answer. All right, now let's move on. A turntable starts spinning from rest at t equals to 0 and accelerates uniformly at 1 radians per second squared to an angular speed of 120 revolutions per minute. How many revolutions does it take to reach maximum speed? There's this new term, revolutions per minute. What does that mean? So when we have, or we talk about full circle, one full circle is equal to 1 revolution, which means that 1 revolution, 1 full circle means, in radians, means 2 pi, right? It gets you, if you're here, in order to go full circle, you start at 0, you get back at 2 pi. So knowing that, we can move forward with the problem. So how are we going to do this? So we have an angular speed. So we have angular speed, which is omega equals to 120 revolutions per minute. And then we have a uniform acceleration, so which is a constant acceleration, which means angular acceleration equals to 1 radians per second squared. Let's go back to the FE handbook, and I'm going to show you a formula for constant acceleration. This is the formula I was talking about. So this formula involves angular speed, angular acceleration, and then the angle theta we have to calculate. Let's go ahead and write this formula down. We're going to say omega squared equals to omega 0 squared plus 2 alpha. And we don't have theta 0, so I'll just write theta. And from this equation, we have to calculate for theta, right? We have to calculate how many revolutions, meaning how many full circles does it take for this to reach maximum speed. So theta is going to be equal to, now omega 0, we have that at t equals 0, and it starts spinning from rest. So which means omega 0 equals to 0. So what we're going to have, we have omega squared equals to 2 alpha theta. And theta from this equation is going to be equal to omega squared over 2 alpha equals 2. Omega, in our case, we have 120 revolution per minute. And then we're going to have radians per second. We have to transform one or the other. So coming here, let me do... I'm going to transform this into radians per second. This angular speed into radians per second. So remember we said 1 revolution is equal to 2 pi, right? In order to make 1 full circle, that means it's 2 pi. Okay, and then we come back here and we say 1 minute is equal to 60 seconds. And now let's calculate that. Remember, your calculators needs to be set in radian mode when you calculate this. Okay, so I'm going to have 120 2 multiplied pi multiplied 60 divided. And I'm getting that angular speed is equal to 12.8 57, and these are radians per second. This is 2 pi radians, right? Because revolution goes away, minute with minute, and then we're left with radians per second. Okay, so now come back here in this equation, and we're going to substitute for omega. We're going to have 12.57 radians per second all squared. And here we're going to have 2, and angular acceleration is 1. So 1, and this is radians per second squared. And let's go ahead and calculate this. 12, 2 divided. Wait a second, I have 12.57 squared, 2 divided. And this is going to give me an angle of 79 radians. The problem is asking how many revolutions. So we have gotten our angle in radians. Now we have to come back and say 79 radians. How many in revolutions? How many revolutions is that? So again, I'm going to say that over here, 1 revolution is equal to 2 pi radians. Okay, so now radians with radians go away, and we have 79, and then 2 pi multiply, and then divided. So I'm getting 12.57 revolutions. This is my final answer. So in order for this turntable to reach its maximum speed, we need it to rotate 12.57 times, or 12.57 revolutions. Or in other words, the closest is 12.5. So the correct answer would be B, 12.5. Great. Let's move to the next problem now. Projectile motion. A cannon fires a shot from the top of a cliff as shown. The muzzle velocity V equals to 240 meters per second, and the angle alpha equals to 40 degrees. What is the range R of the cannon? So range is shown here as being this horizontal distance, which if you look in the FE handbook, I'm not sure if that's shown, it's also notated as X. And then this is your vertical distance Y. So let's go to the FE handbook and see what are you given on projectile motion. So you have your X and Y, and you have the speed and then the theta, so not very much. Whenever working with these problems, we're going to use a lot this equation and then this equation. So let's come back here. And from the beginning, before you start, we have to set our coordinate system. And to make the things easier, you want to set your coordinate system at the point of, or at the starting point. Let me do, so this is going to be Y, and then this is going to be X. And I'm going to tell you why it is easier this way. And remember, we have to make sure that whenever we have a distance above the X line, that's going to be positive, or on the right, it's going to be positive. And whenever we have to go below the X axis, we're going to have a negative distance. And same with the on the right of Y axis. On the left of right axis, we're going to have a negative value. So keep that in mind. Now, let's see what are we given. We have the velocity, we have the angle. We're asked to calculate the range, the X distance, from the starting point all the way until the it hits the ground. Okay, so as I mentioned before, we're going to use these two equations, which represent the horizontal and the vertical distance. So let's write them down. I'm going to say here x is equal to, we have x0 plus v, and this v, this is our v, the speed, right, which is 240 miles per hour. And then we have the x and y component of this v, because this particle moves horizontally and then vertically. So the Vx, which is equal, since this is angle alpha, it's going to be equal to V cosine alpha. And then Vy, it's going to be equal to V sine alpha. So let's go ahead and do this. X equals to x0 plus V cosine alpha multiplied by t. This is our x. And now, based on this equation, I would like to lay out everything that we know and everything that we don't know. So we have x. X is actually what we have to calculate, this range. So x we don't know, we have to calculate. Then x0, now x0 is equal to 0. This is why I like to place my axis right at the starting point, because it gets rid of this term. If we were to place this, let's say here, right, our axis, if we would know this distance, let's say, I don't know if it's 1 or 2 meters, then our x0 would be -2 or 2, excuse me. So if we were placed the coordinate here, our x0 would be this distance from here, from starting point to whatever we placed our coordinate system, the horizontal distance. So this is why I'm going to delete this. This is why I like to place, and I suggest you place the coordinate system right at the starting point. Now, this is 0. I'm going to write this down. x0 equals to 0. V, we have V is given in the problem as 240 meters per second. And then alpha is also given as 40 degrees. And T, I don't think we are given T. So we don't have T. We have to also calculate T. So we cannot calculate this X because we are missing the time, how much time it takes for this to reach the ground. Okay, now let's go back to our second equation, which defines the y distance. And let's write it down. Gonna come back here, take the same color. So I'm gonna kind of draw a line, vertical line. So now I'm gonna write y is equal to, and I'm gonna write it in the same order, y0 plus v. This case we have v sine alpha times t. And then, so I wrote v0 plus v0, y0, excuse me. y0, it looks like v because I have all that blue there. So y0 plus v0 sine theta times t. I think I wrote that down. There you go. Then we have this member here, minus gt squared over 2. Let me write this down. Minus gt squared over 2. So let's see, what do we know? Let's start. Okay, so y is equal to, and now let's see how much is y. We have this value from the point from the starting point all the way to the instant it hits the ground. This is our y, and since it's below the x-axis, remember we have to consider a sign. Y equals to minus 92 meters. Next, Y0 is 0. Remember, because we placed the axis right at the starting point. So X0 and Y0, we got rid of them. They are 0. If we were to place our axis here, we're going to have our Y0 as 92, right? But we don't want to do that. So Y0 equals to 0. V, we have V as 240 meters per second. We have alpha as 40 degrees. And again, we don't know T. G is the gravitational acceleration, and G is positive going downwards. In our case, since we're going upwards, G is going to be negative. Thus, the sign here given in the formula. Because usually you see this formula written as something like this: Y0 plus V sine alpha t plus a acceleration multiplied by t squared over 2. And then you have to write down that the acceleration equals to gravitational acceleration, and it's negative due to the fact that it goes upward. So you add this minus. Now, they in the FE handbook already have considered that for you, so you don't have to think about that. So G is going to be equal to 9.81 meters per second squared. And T, we said we don't know. So we have two equations, 1 and 2. And we have two unknowns. Let me circle. We have first unknown and the second. And then T is the same. So we have to calculate X and T. So looking here at this Y equation, I have one unknown. The only unknown is T. So I'm going to calculate T from the Y equation, and then I will substitute it in the X equation and find out for X with the range. Let's do that. Okay, let's see. I'm going to come here with the Y equation. I'm going to write down Y is equal to V sine alpha multiplied by T minus G T squared over 2. And now let's substitute. Y is equal to minus 92 equals to V is 240. All right. And then we have sine of 40 degrees multiplied by T minus 9. Oh, I wrote, oh, that's G. Minus 981 multiplied by T squared over 2. Okay, so now we can simplify this a little bit. So I'm going to do minus 92, and I will take everything on one side. So let's calculate for this member. This is going to be 40, and this is in degrees. So you know what? I have to mode. I will do degrees. So I have 40 sine, and then 240 multiplied. Okay, so if I take this on the other side of the equal sign, that's going to give me a negative value of 154.3 T. And then if I take this member on the other side of the equal sign, it's going to become positive. So I have 981, 2 divided. We have plus 4.9 T squared. So this is a quadratic equation, and we have to solve for T. If I was to reorganize this and put it in the right order, I'm going to get the following. So 4.9 T squared minus 154.3 T minus 92 equals to 0. Same here, equals to 0. Okay, so if you calculate for delta, I'm going to quickly do delta. It's going to give you, or let's do solutions T1 and T2. You're going to get minus B, which in our case, this is B. I'm going to have 154. It's going to be positive. So I'm going to have 154 because the formula calls for minus B. We have minus 154 minus it's plus. Minus square root of delta. If you calculate delta here, you're going to get delta. I'm not going to do that because it's going to take me too much time and I don't have enough space. So square root of delta is equal to 160 approximately. So we're going to use this value minus 160 over 2a. 2a is 4.9 multiplied by 2, and this gives you 9.8. So this is T1, and T2 is 154.3 plus 160 over 9.8. So if you notice this value, it's going to be negative. So we cannot use this value. T cannot be negative. So this is not our option. This is going to give you T2 is equal to 3207 seconds. So this is greater than 0, which means it's a solution for us. So the T is the time this particle reaches the ground is 32.07 seconds. So now that we know T, we can come back to X equation and calculate for X. I'm going to squeeze it over here. So X is going to be equal to V, which is 240, multiply cosine of 40, or 32.07 equals. Let's use the calculator. We have 240, 40 cosine multiplied, 3207 multiplied. And I get a value for X as 5,896.09. And these are meters. Okay, so I got the closest is B. I think the problem uses, instead of 3207, it uses just 32. So they get 5,883, which it doesn't matter because you still get this value close to the option B. So if you were just go back and say 40 cosine 240 multiplied 32 multiplied, you would get exactly 5,883. I use some decimals, but it doesn't matter. Anyway, the correct answer is B. Let's move on. Now we're going to work on some rigid bodies kinematics, mass, moment of inertia. A prismatic rod with mass 5 kilograms is supported by a frictionless hinge at a distance 65 centimeters from the left end as shown. The rod is held static in the horizontal position as shown and released from rest. What is the acceleration of the left end of the rod upon being released? So the question is, what is the acceleration of the left end of the rod upon being released? So let's imagine what's happening. This rod, it's held in equilibrium, and then upon release, we're going to have this movement. This is going to go down, and this side is going to go up. Now we know from FE handbook that radial transverse acceleration is equal to R multiplied by angular acceleration. So here, upon release, we're going to have a transverse acceleration going upward. Going to the FE handbook, the transverse acceleration in velocity is, the formulas are given under the circular motion. And the formula for the transverse acceleration is A equals to R alpha. So I would like to come back here and write down that A is equal to R multiplied by alpha. R in a circular motion equals to the radius. In our case, R is the distance from the hinge to this end. This is the R. This is because we are asked to calculate the acceleration of the left end. So R is going to be equal to 0.65 meters. Now we have to figure out what is alpha. Alpha is angular acceleration. There are a few things we can apply here, but the first thing that I can see that I can do is use the equation of dynamic equilibrium. And that looks like this. Moment, or the resultant moment, is equal to mass moment of inertia multiplied by angular acceleration. Now, the resultant moment, we can calculate it. If we come back here to this rod has a weight at the midpoint, right? And the weight, we're given the mass as 5 kilograms. So if I come back here, we have weight is equal to mg, right? So we have the mass as 5 kilograms, and g is 9.81 meters over seconds square. So this gives me a weight. Let's see, we have 981, 5 multiplied. So this is going to give me 49 newtons. Okay, so now this is the weight pointing at the midpoint of the rod. And if we want to calculate the moment about the hinge, this moment is going to be equal to the weight multiplied by this distance. Let's call it D. And now D, so I'm going to do 49 newtons multiplied by D. The length of the entire rod is 2.7. And if we divide this by 2, we have 1.35. So this distance over here is 1.35. And this distance over here on the other side is also 1.35. So in order to find out D, we have to take 135 and subtract 0.65. So I'm getting that D is equal to 0.7. So here I'll have 0.7 meters equals 2. So I'm getting that the resultant moment is 34.3 newtons meters. So now we have the moment. Let's try and calculate the mass moment of inertia. Luckily, you don't have to memorize them because in the FE handbook, you are provided with some regular shapes or formulas for the regular shapes. So the mass moment of inertia for this rod about this hinge, let's go to the FE handbook and look for the formula for the mass moment of inertia. And you can just do a search. I'm going to say mass moment of inertia, and it's going to lead you to this formula over here. And this is the formula we're going to use. And this formula is for an object, let's say, or a mass. This is the center of gravity. And we have to calculate the mass moment of inertia about this axis. And there's a distance D between these two axes. So let's see. We're going to go back. Let's see. Let's write this formula down. We're going to say that I is equal to, we're going to do IC plus, and it's mass multiplied by D squared. Okay. So now let's look for in our case, we have a prismatic rod. So we have a rectangle for the cross-sectional area. So you have to be careful here. We're going to go at the end of the dynamics. There is a section with some regular shapes and formulas of mass, moment of inertia. So let's go and look for our, this is for a thin plate. In our case, we have a prismatic rod. So I'm going to use this formula for the mass, moment of inertia. So we're going to have mass multiplied by d squared, which is the length of the rod in our case, divided by 12. So this is going to be equal to mass multiplied by L squared divided by 12 plus, I'm going to do lowercase mass plus mass multiplied by d squared. Now let's substitute. I'm going to come back here and say results I is equal to, now mass is 5 multiplied by L, we have 2.7 meters squared over 12, plus, again, we have 5 multiplied by D. D is the distance from the center of gravity of this rod about the hinge. So again, D is going to be 0.7 squared. Doing this calculation, you're going to get a mass moment of inertia equal to 5.49 kilograms times meters squared. So now that we have the resultant moment and mass moment of inertia, we can come back here to this equation and calculate for angular acceleration. From this equation, angular acceleration is going to be equal to the resultant moment divided by mass moment of inertia. And from here, we're just going to substitute. I have 34.3 newtons meters divided by 549 kilograms meters squared equals, or results, angular acceleration is equal to 6.25 radians over second square. All right, so now that we have angular acceleration, we can come back to this initial formula and calculate for the transverse acceleration. So I'm going to write this here. Transverse acceleration is going to be equal to R, which we discussed is 0.65 multiplied by 6.25. And this is going to give you a value of 4.06 meters over seconds squared. So the correct answer is C. Next problem is something similar to this problem, but we're dealing with a metallic disc. So the problem says a metallic disc of uniform thickness having mass 3 kilograms is suspended from a frictionless pin as shown. If the force of 200 Newton acts as shown below, what is the instantaneous acceleration at the point of application of the force? So in this case, we're going to apply the same principles. We're going to have that the transverse acceleration is equal to R alpha, where R, in this case, remember in our previous problem, R was the distance from the hinge, right, to the end of the left side of that rod. So this was our R. In our case, here we have the application of the force, and then here we have the hinge. So the distance, our R, is going to be this distance over here, which we're going to have to calculate. This is R. And now alpha, we're going to apply the equation of dynamic equilibrium, we're going to say m equals to I alpha. I think my pen is already tired. Yeah, it doesn't really want to write anymore. This is a too long video, even for my pen. You know, and I haven't mentioned where is this equation. You can find this equation of dynamic equilibrium is here in the FE handbook. And let me go down a little bit more. And here you're going to find MC as I alpha, where I is mass moment of inertia and alpha is angular acceleration. I found it somewhere. So for rotation about some arbitrary fixed axis, sum of MQ equals to IQ alpha. Okay, so let's see how are we going to solve this problem. First, I suggest, let's see, what is the moment about, let me delete this. So, okay, let's see. So the moment, I'm going to start with the moment M is equal to, we have the force. So it's going to be equal to the force that we have multiplied. So this is the moment by the hinge, right? So I have the force multiplied by D, and in our case, D is this distance over here, 110 millimeters. So I'll say D, and this equals to 200 newtons multiplied by D. I'm going to transform it into meters. So I have 111 meters. So I'm going to get a resultant moment of 200, 0.11 multiplied 22 newtons meters. So I've got my resultant moment. Now I have to calculate the mass moment of inertia. And I guess this is a good exercise for you to practice calculating mass moment of inertia for different shapes. So I equals to, again, we have, this is we have to calculate the mass moment of inertia about the hinge. So we're going to have the mass moment of inertia about its central axis plus the mass multiplied by distance squared. So let's see, we have a metal disc. Okay, this is our shape. I'm going to go all the way down to the end of dynamic section, and we're going to try to find our metal disc, thin circular disc. There you go. This is our shape. So we need the moment of inertia about Z axis. So we're going to use this one over here. So let's write this down. I'm going to change back the color. So moment of inertia is 1, about the center is 1/2 m, which is mass, r is the radius, squared, so I'll do r squared, plus mass multiplied by the distance squared. And the distance is from this point about the hinge, so it's 110 millimeters. So d squared equals mass moment of inertia is equal to 1/2. The mass is 3 kilograms, 3 kilograms multiplied the radius. Now the radius is actually this distance over here, 30 millimeters plus 110 millimeters, which is 140 millimeters. That comes up to 0.14 meters. Plus mass is 3 kilograms multiplied by D, and D is the distance from the center about the hinge. So it's this distance D, which is 0.11 meters squared equals. This is squared. Let's not forget that. And then this is also squared. Okay, let's do this calculation. So the mass moment of inertia is equal to 0.0657, and the units are kilograms or meters squared. So again, now we have the moment. We have the mass moment of inertia. We're going to come back to this formula over here and calculate for the angular acceleration. Angular acceleration. It's going to be equal to resultant moment over mass moment of inertia. And this is going to be 22 divided by 0.0657 equals to 334.85, I'll say 9. And these units are radians per second squared. And again, we have now angular acceleration. Let's calculate for r. How can we calculate r? If you look here, it is very clear to see you're going to have a right triangle. These are going to be the two cathetes, and r is your hypotenusa. So r is going to be equal to uppercase r squared plus this distance, which is d squared, equals to, this is going to be 0.14 squared plus 0.11 squared. My goodness. Okay, squared equals 2. So you are going to get r, let me see, 0.14 squared, 0.11 squared plus square root. So I get a value for r, 0.178. 0.178 meters. Okay, so with r known, with angular acceleration known, we can come back to this initial formula and substitute. Of course, I'm going to have to make this a little bit smaller here. Let me just square root like that. So we can come back here and say that the acceleration, final acceleration, is equal to 0.178 multiplied by alpha. Angular acceleration is 334.9, and this is going to be 334.9 multiplied. I'm going to get an acceleration 59.63, and these are meters per second squared. So 59.63 is approximately 60. So the correct answer is going to be C. All right, guys, that is it for today. I hope you have fun with these problems. I'll see you next week.